All right, welcome to this explainer. Today, we are tackling what is arguably one of the most powerful and honestly fascinating concepts in all of calculus. We're setting up a genuinely incredible mathematical goal for ourselves, taking complex, unpredictable mathematical functions and turning them into clean, infinitely long power series. Think of it kind of like taking a highly complex machine, stripping it down, and figuring out how to rebuild it perfectly using only the most basic, fundamental building blocks. By the end of this explainer, you're going to understand exactly how we pull off this mathematical magic trick.
So let's dive right into this mission. Our central focus today boils down to one big, bold question. Can we genuinely represent a function, like any function f of x, as a power series? To solve this mystery, we really have to break it down into two very distinct parts. Question 1, what would that power series actually have to look like? And then question 2, which is honestly the real hurdle here, how can we actually prove that our newly built series truly equals our original function? We're going to tackle these one at a time.
To kick off our little mathematical interrogation, we're going to do something mathematicians absolutely love to do. We are just going to assume our suspect exists. Let's suppose that our function f can in fact be represented by a generic power series centered around some arbitrary number a. So f of x equals c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared, and so on and so forth. Right now, all those c coefficients are completely unknown to us. They're basically wearing masks. So our immediate goal is to force those unknown coefficients to reveal their true identities, using nothing but the original function f. Now, let's see how this builds an incredibly satisfying rhythm. How do we unmask these guys? Well, first, we just substitute x equals a directly into our equation. All those terms with x minus a, they instantly vanish, leaving us with just c sub 0 equals the function evaluated at a. Boom, first mask removed. Next, we take the derivative of the entire series and then plug in x equals a again. This time, everything vanishes except c sub 1, revealing that c sub 1 is simply the first derivative, f prime of a. And you know what? We do it again. Take the second derivative, plug in a, and we find that c sub 2 equals the second derivative of f at a, all divided by 2 factorial. We just keep peeling back the layers by taking successive derivatives. If you keep repeating that process, a really striking, undeniable pattern emerges. Our key discovery here is this. The nth coefficient, c sub n, is always going to be equal to the nth derivative of the function evaluated at a divided by n factorial. What this ultimately means is that a power series representation is completely restrictive. These coefficients can't just be any random numbers we want, no way. They are absolutely forced by the function's own derivatives.
So, now that we know exactly what the series must look like, it is time to formally introduce our primary suspect by its real name. When we build a series using these highly specific, derivative-based coefficients centered around any number a, we officially call it a Taylor series. That's the big, overarching term. But if we decide to center our series specifically at 0, meaning a equals 0, it gets VIP status and its very own special name, the Maclaurin series. So a Maclaurin series is really just a Taylor series that happens to be centered at 0. Simple as that. Okay, brace yourself, because here is the major plot twist of our mathematical detective story. Having a Taylor series does not automatically mean that it represents your function. Take a second to let that really sink in. Just because a function is infinitely differentiable, and just because we went through all the hard work of successfully building this beautiful Taylor series, it doesn't actually guarantee that the infinite series mathematically equals the original function.
And this brilliantly illustrates our anomaly. Consider this very specific, kind of strange function. F of x equals e to the power of negative 1 over x squared. If you take all of its derivatives at x equals 0, they evaluate to exactly 0. So if you go ahead and build its Taylor series, it's literally just a string of zeros. But the actual function itself is absolutely not 0 when x isn't 0. The math worked perfectly to build the series, sure, but the series completely and utterly fails to represent the function.
This terrifying realization brings us directly to our second big question from the very beginning. How do we actually prove that a Taylor series genuinely equals our function? Well, to do this, we have to introduce a new concept called the remainder, denoted as r sub n of x. The remainder is essentially just the error. It's the exact difference between our true function, f of x, and our finite Taylor polynomial approximation, t sub n of x.
Let's break down this burden of proofs so it's crystal clear. You can frame any true function as being equal to your finite mathematical approximation, which is the Taylor polynomial, plus whatever leftover error remains. It's that simple. So, If we want our Taylor series to perfectly equal the function, we need that error, that remainder, to completely vanish. Enter Taylor's theorem. This is basically our mathematical magnifying glass for measuring the exact size of that error. The theorem states that the remainder is equal to the n+1st derivative of the function evaluated as some mysterious number c divided by n+1 factorial, all multiplied by x minus a to the power of n+1. Okay, I know. It looks like a terrifying mathematical monster, but what it really gives us is a concrete boundary. It lets us put a firm lid on how big the error can possibly be. So the crucial point is this. To finally close the case and confidently declare that our Taylor series perfectly equals our original function, we need that error to shrink to absolutely nothing. In calculus terms, we must prove that the limit of the remainder, r sub n of x, as n approaches infinity, equals exactly 0. If the error goes to 0 as we add an infinite number of terms, then, and literally only then, does the Taylor series perfectly represent the function.
Let's bring in a concrete lineup so we can see this in action. Take a true classic, the sine of x. We start by evaluating the function and its derivatives at x equals 0. Sine of 0 is 0. The derivative is cosine, which gives us 1. The next derivative is negative sine, giving us 0 again. Then negative cosine gives us negative 1. And then it repeats, 0, 1, 0, negative 1. The derivatives beautifully and predictably cycle like that forever.
Now, because every even derivative evaluates to 0, all the even power terms in our series completely magically disappear. We're left building our Maclaurin series directly from that alternating sequence of 1s and negative 1s on the odd powers. So sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on to infinity.
But remember, we still have to prove it actually equals sine of x. Using Taylor's theorem, we look at the remainder. Because the derivatives of sine and cosine can never physically be larger than 1 or smaller than negative 1, the numerator of our error term is capped. Because of this, as n goes to infinity, that massive factorial in the denominator completely overpowers the numerator, causing the whole error fraction to cleanly approach 0 for absolutely any value of x. Therefore, the series perfectly represents the function everywhere. We say the radius of convergence r is infinity.
Now, sine is definitely a best-case scenario because it converges everywhere, but that is not always true. We really need to contrast the mechanical act of deriving the series itself, finding those coefficients using Taylor's formula, with finding where the series is mathematically legally allowed to operate. Just because we have a series doesn't mean you can plug any x value into it willy-nilly. We have to find where it converges, and to do that we rely heavily on the ratio test from earlier in calculus.
Let's look at a rapid-fire example of this limitation. If we had a completely different function in series, say one centered at a equals 4, and we ran it through the ratio test, we might find that the limit dictates the series is only valid when the absolute value of x minus 4 is less than 3. This means our radius of convergence, r, is 3. The series mathematically falls apart and becomes useless garbage if you try to plug in an x value that is more than 3 units away from that center point of 4.
This perfectly summarizes our entire journey today by strictly separating two completely different realities. First, a function simply having a Taylor series. That's just a mechanical process of taking derivatives. But second, the series actually representing the function. This is a much higher bar. This only happens when you can mathematically prove that the remainder, the error, actually goes to 0. Which brings us to our final thought for today. Finding the Taylor series is literally only half the battle. Writing down coefficients is neat, but the real detective work is proving that the series genuinely represents your original function by eliminating that error. So, the next time you see a neat, infinite polynomial, you have to ask yourself, is this truly the function in disguise, or just some mathematical imposter? Keep questioning, and I'll see you in the next explainer.